Yes. Can you hear me? Is this microphone working? Can you hear me? Yes, great. So it's really a pleasure to have a chance to present this work I very recently completed with Aviv, in which we put into context the abundant population of ultra-diffuse galaxies that have been discovered in clusters, showing that these are the tail into the low surface brightness regime of the population of dwarf galaxies. But let me start from the beginning. So a few ultra-diffuse galaxies were already known in the Coma and the Virgo cluster, but it has been thanks to the Dragonfly array that the full population of them has been first discovered in Coma. So Peter van Dokkum and collaborators identified 47 of these galaxies that are very faint, with median stellar masses of only 6 times 10 to the 7 solar masses, but extremely diffuse for their luminosity, with effective radii that are larger than 1.5 kiloparsec and reach up to 4 or 5 kiloparsecs in size, and therefore having very low surface brightnesses. The properties of the population identified by van Dokkum et al. Are rather extreme, and you can see in this plot where they are located in the plane of absolute magnitude against effective radius, where diagonal lines are lines of constant surface brightness, and compare them with the population of normal and bright galaxies of the Coma cluster. So as you can see, the UDGs may appear as a separate population of large and very low surface brightness galaxies. However, soon after the van Dokkum result, using Subaru, Koda et al. Showed that the UDGs are actually even more abundant in Coma, identifying a population of approximately 1,000 of these galaxies with equally low surface brightness, but perhaps less extreme sizes. And what I should mention here is that although the population of UDGs and normal bright galaxies appears separate in this plot, this is just a result of observational effects, and that are generating essentially the gap that you can see between the two populations. So since their detection in Coma, it has been established quite clearly that UDGs are ubiquitous in nearby galaxy cluster. They have been detected in the Fornax clusters, they have been detected in the Virgo clusters, but also in all 8 of other nearby clusters that have been observed with CFHT. So we have seen UDGs have stellar masses of dwarf galaxies, but actually their smooth spatial distribution in the cluster shows that they have not all just been accreted, and therefore that they can survive the cluster tides, at least for some time. As such, it was soon realized that they need to be strongly dark matter-dominated systems. So, of course, the question here is how to form such galaxies, how do UDGs form? And although this illustration is not representative of the mean properties of the population of UDGs, it shows very well how fluffy and how diffuse these galaxies can be, with luminosities of a puny dwarf, but the sizes of a Milky Way. And in fact, one of the formation scenarios that has been first proposed is inspired by this comparison, and proposes that UDGs form because of the cluster environment, that there are galaxies that infall on the cluster very early on, and have the star formation shut down by the cluster itself, by gas removal, for example, from ramp pressure stripping. In other words, UDGs are failed galaxies that live in halos that are more massive than their luminosities, more massive than suggested by their luminosities at least, and likely as massive as the halo of the Milky Way. So what I'm going to show today is instead that the formation of UDGs is unrelated to the cluster itself, and that they are to be expected in the field too, that they are indeed dwarf galaxies, like suggested by the stellar masses, and their large sizes, and therefore low surface brightness, are compatible with the same model that describes the population of normal bright galaxies. So, of course, one of the possible ways, and possibly the best way, to distinguish between these two scenarios would be to measure the dynamical mass. This is, however, very hard, as you can imagine, because the surface brightnesses are very low. And in fact, we only have a single mass measurement for UDGs, this VCC 1287 that is located in Virgo, that has been obtained using globular cluster spectroscopy. So this measurement shows that this single UDG has in fact the virial mass of a dwarf galaxy with only 8 plus or minus 10 to the 10 solar masses, despite the fact that it has a very large effective radius of 2.4 kiloparsecs. This, of course, is, however, just one system that has been measured with only 7 globular clusters. So the idea of our letter with Avi was to test the formation scenarios of UDGs using, instead of their individual masses, the properties as a population. So there are two independent pieces of information that we can use here that have both been provided by Vanderburg et al. Essentially less than 2 months ago. So the first is the abundance of UDGs in clusters of different virial masses. Like I'm showing here, black and red show two different selection criteria used to identify in observation operationally the population of UDGs. And the second piece of information is the size distribution of UDGs within subpopulation that are defined by different surface brightness cuts, like I'm showing here with different colors. So what we have done has been to construct predictions for these measurements using a very simple semi-analytical model that matches the corresponding quantities for normal bright galaxies. So the model is indeed very simple. So given a cluster and its virial mass, we construct its model galaxy population. So first we use Monte Carlo generated lambda CDM accretion histories for the cluster that we use to populate it with galaxy halos having lambda CDM properties. And then we paint galaxies onto each of these halos using a standard abundance matching recipe to get the stellar masses, and importantly, assigning galaxy sizes according to the standard model of disk formation. So according to this model, the size of a galaxy is determined by the angular momentum, or spin parameter lambda, of gas and halo. So gas and halo acquire the same angular momentum before collapse because the torques from the large-scale structure that impart it operate very similarly on both of them. But after that, the gas, of course, collapses into a rotationally supported disk, the size of which reflects the initial spin parameter of the halo. So which is just a result of angular momentum conservation. So therefore, in this very simple model, at a given halo mass, the distribution of galaxy sizes reflects the distribution of halo spin parameters, which has been measured very well in cosmological simulation. And although very simplistic, this model describes pretty well the population of normal bright galaxies. So here, for example, I'm showing data for the extended Virgo cluster surveys, showing both the absolute on the left and relative or normalized specific galaxy sizes distribution in Virgo. And here you see how our fiducial model matches very well this data, recovering both the total number of galaxies in a Virgo-sized cluster and their specific size distribution on the right. So now, given our model cluster galaxy population, we can construct prediction for the abundances of UDGs by essentially applying the same selection criteria that were applied on the observation to define the observed samples, which I'm showing here essentially with different colors, the Vanderburg sample and the Coda sample. And as you can see, the prediction of our simple semi-analytical model matched the observed UDGs very well. So similarly, we can do an analogous exercise trying to recover the steep size distribution that has been observed in cluster. And here you have on the right, on the left, the data, and here the model that recovers very well the measured power law slope of approximately minus 3.4, and at the same time recovers the fact that the distribution of UDGs is essentially flat in surface brightness, meaning that if we select two different bins in surface brightness with the same size, we find more or less the same number of UDGs in both of them. So what are the physical implications of this model? What are the physical properties of the UDGs? So here I'm showing the plane of galaxy halo mass against the galaxy stellar mass on the left, and the plane of halo spin parameter against halo concentration on the right. And in each of these planes, I'm also showing the means with scatter of the full galaxy population. So this is the abundance matching relation on this side, and here you have means and scatter on the spin parameter and means and scatter on the concentration, together with the location in these planes of the population of bright galaxies, which is essentially the extended Virgo cluster catalog. So this is how this compares with where the UDGs are, with the physical properties of the UDGs. So as you can see on the left, according to this model, the UDGs, which are in green and red, again, the Vanderburg and the Coda sample, follow the abundance matching relation, but they are essentially dwarf galaxies. So galaxies that are hosted in halos of at most 10 to the 11 solar masses, although this number, of course, depends on the abundance matching relation that is used, that might be somewhat uncertain. And as you can see on the right, what is actually differentiating the UDGs from the normal galaxies is their halo spin parameter that is causing them to be larger and therefore lower surface brightness. So as I was mentioning before, none of the ingredients that I'm using here tied UDG to the cluster itself. In particular, the distribution of halo spin parameter has been measured by cosmological simulation, and in lambda CDM is independent of environment, which means that the most direct prediction that we can do with this model is that UDGs should be observed, are to be expected in the field too. And in fact, just a couple of weeks after we submitted our letter, a paper came out using data from Stripe 82 and finding UDGs essentially across environments around, in the large scale structure around the cluster Abel 168. So they're finding UDGs both at very high environmental densities, that is in the core cluster, and outside it in filaments and in the groups, and also in the field itself. And interestingly, what they have been also trying to do is to characterize their mean halo masses by comparing their spatial distribution across environments with the distribution of dwarf galaxies and the distribution of L-star, then massive halo, galaxies that are hosted in massive halo. And what they find is that while the UDGs are very aligned, their spatial distribution is compatible with the spatial distribution of dwarf, they show significant differences with the spatial distribution of L-star galaxies, offering support to our model from a completely independent point of view. And here are my conclusions. So UDGs are ubiquitous and numerous in both clusters and in the field, and that's because their formation is independent of the cluster environment itself. They are dwarf galaxies rather than hosted by Milky Way halos, and they represent the tail into the low surface brightness regime of the abundant population of dwarf galaxies. And we can recover their population properties, both abundances and side distribution, just using the same model that predicts the properties of the bright galaxy population. And I'll stop here. Thank you. So, of course, the best is continuing along this line with globular cluster because it's very difficult to get stellar resolved spectroscopy. I mean, another way is just to count the globular clusters in the halos of these galaxies because the number of globular clusters is also a good indication of masses. So I guess we'll have more of this in the near future.
Comment about this. Globular clusters might not be a very good idea for low massive galaxies because it's well known that for dwarfs, they actually accrete because of dynamical friction in much less than a Hubble time. So that's why dwarf galaxies have very few clusters. So, and probing the mass with 7 points, it resembles a bit the first work. I don't know if you know this one. The first mass estimate of, I think it was a Draco galaxy, like in the late 80s or early 90s, was done using 2 stars. They said, okay, we see 2 stars, and their radial velocities are too far apart to be explained without the dark matter. This was the right guess, but this was not a measurement.
Yes, well, the globular clusters that have been used here extend out to 8.1 kiloparsec. So the farther one is 8.1 kiloparsec. But I agree absolutely that 7 kinematic measurement is definitely not enough. And that is why we, rather than using massive, we use the population property to constrain their nature. Okay, there we go. Okay, there we go.
Okay, so sorry for all the affiliations, but this is a sabbatical year. Okay, so the question I want to ask. Oh, I guess it's cut off. That's not so good. Oh, it's okay. Maybe I'll just use this and not full screen. It's cut off for some reason. So the question I want to ask is whether baryons follow dark matter. So the answer is no, because baryons are affected by other things other than gravity. But more interesting question is whether the baryons maybe follow dark matter on large scales. And even there, the answer is maybe more surprisingly no. Okay, so I'm sorry I can't use the full screen, but I'll just go like this. So the basic idea, the basic reason is, the basic physics is simple. It's in the early universe before cosmic recombination. The photons underwent sound waves, acoustic oscillations, and with a sound speed of order the speed of light. Dark matter was following gravity, was accumulating in over dense regions. The baryons were still, the atoms were still ionized, so the electrons were scattering with the photons and being carried along with the photons in the acoustic oscillations. So then the universe cooled and recombined, and hydrogen atoms formed. So when the hydrogen atoms, of course, they're neutral, so they didn't scatter so much with the photons anymore. They decoupled and started falling towards the dark matter concentrations due to gravity. So as a result, when the atoms formed at recombination, the distribution of baryons was quite different from the dark matter. And afterwards, as I mentioned, due to the mutual gravity, the baryons and dark matter caught up with each other, but they never did it completely. So this is a plot here of how they catch up. So let's look just at the upper plot. This is a ratio between the baryon to the dark matter perturbation, or fluctuation, typical fluctuation, as a function of scale or a wave number down here. And these are a different redshift. So redshift 400, you see the baryon fluctuations are still around the 10th, so here is 0.1 of dark matter. And then they catch up, redshift 100, redshift 20. Now there are different regimes. These are 8 orders of magnitude of scale. So if we start from very, very large scales, outside the horizon at matter radiation equality, there baryons and dark matter always follow each other because there's no physics other than gravity. Now inside the horizon, you have the BAO scale of baryon acoustic oscillation. So that's around 100 megaparsecs, where these strong acoustic waves, sound waves in the baryons, give them a difference compared to the dark matter. And again, slowly the difference diminishes because they attract each other. Then there's on slightly smaller scales, but over a wide range of scale, which is something we call large-scale structure, you see that baryons are have smaller fluctuation than the dark matter, but the ratio is a constant. And finally, at the smallest scale, you have the genes of filtering scales where the pressure of the baryons of the gas gives you basically sound waves of the gas, and these sound waves prevent the gas from accumulating on very small scales, and that's the genes cutoff. Yeah. Okay, so Avi and I wrote this little paper in 2011 called the Scale-Dependent Bias of Galaxies from BAOs. So we were looking at predicting an after effect of this early, I just showed very high redshift, predicting an after effect for the current universe, based on the varying gas fraction in galaxies. So the basic idea is that, as I just showed you, the baryon to dark matter ratio varies, and I'll show in a second that this is left over at low redshift. But if you have more baryons or more gas in some region than average, you would expect that when galaxies form in halos in this region, they'll on average have more gas within the halos. So presumably, on average, a halo with more gas will have more stars, and will have a lower mass to light ratio compared to other regions. So this is the qualitative picture, but more important is the quantitative picture. So there are some details here about star formation, maybe feedback, complicated stuff. But if you look on large scales, when perturbations are linear, so you have some overall amplification factor, some overall bias factor, which we don't exactly know how to predict. But the quantitative issue is that the pattern we do know. So we know very well from the initial perturbations what should the pattern look like for the baryon to, and actually what matters is not to dark matter, but to the total matter. So the total matter is what determines gravity and determines how many galaxies form. But the baryon, the distribution of baryons, which is slightly different, determines, or at least affects how much stars, how much gas you have and how many stars per galaxy in different regions. So this relative pattern of how the baryons are differently distributed from the total, we know very, very well. And the same pattern should manifest itself, should appear at some level if you look at the pattern of luminosity to mass ratios in the universe of galaxies. So here's the way it looks at low redshift. So what I'm plotting here, again, is a function of scale, but here focusing on the BAO scales. This is R of k. It's the difference between the baryon and total matter fluctuation in relative units. So how different are the baryons? It's always a negative number because the baryons are still slightly under perturbed compared to the dark matter fluctuations. You can see at redshift 6 it's a couple percent effect, and down to redshift 0 it's like a 0.5% effect. And it varies, it maintains its shape with redshift, but declines in magnitude. However, there's an amplification of this effect. So when Avi and I were writing this paper, coincidentally I was at the same time writing a paper with my former student, an ITC person, Smadar Naoz. So we were actually looking at a completely different thing, about redshift 15 or 20, doing numerical simulations with Naoki Yoshida, and looking very carefully at these initial conditions for gas as being different from dark matter, and trying to see how that affects actually the amount of gas depletion that you get in very small halos around the genes or filtering mass. That's what we were looking at. But during this time, I noticed that in our simulations, we had some halos that were much heavier than the small values around 10 to the 5 solar mass that are affected by the gas pressure. But even in very heavy halos, there was gas depletion. And these are the points for like 10 to the 7, 10 to the 8 solar mass halos, which shouldn't have missed any gas compared to the cosmic baryon fraction. But they were missing, and I think it's because we had the right initial conditions. And indeed, this thing was decreasing with time, as you expect, based on this this relative difference in the baryon to total matter fluctuations. But you can see instead of at these redshifts, instead of a 5% effect, it was like a 15 to 20% effect. So there seems to be like an amplification by about a factor of 3. And that makes sense. So when galaxies form, they reflect how much gas there was in the large-scale region. But halo formation is a nonlinear process, and we don't know exactly what happens. So at least based on these simulation results, there seems to be an amplification by about a factor of 3 of this effect during galaxy formation. So 5% missing baryons on large scales means 15% missing inside a halo. So that just gives us a rough idea of of the magnitude of the effect. Now, my paper with Avi actually didn't get much attention, but hopefully now it will get more attention, because so the two of us, along with a number of other people, we tried to search for this in data for the first time. So this was actually led by Maayan Sumainak, who was a PhD student of Ofer Lahav's, and now she's a postdoc at the Weizmann Institute. So we took some BOSS data and searched for this effect. But even more importantly, during this work, we realized that this effect is much more important than Avi and I realized. So Avi and I realized that if you measure this effect, you would measure this kind of bias factor of how much does galaxy luminosity depend on delta, the difference between baryons and total matter. This would be kind of a novel aspect of galaxy formation. But now we realize that this would be much more important, because the most important thing it would be a kind of linear theory, linear regime bullet cluster. So here's a bullet cluster where the dark matter, based on weak lensing in blue, the dark matter is seen to follow the galaxies and not be concentrated like the gas. And this is supposed to be nice direct evidence for dark matter. However, the clusters are highly nonlinear complex objects. So there's also on the other hand the train wreck cluster, where the dark matter does seem to be concentrated with the gas and not following the galaxies. So this maybe is evidence against dark matter, or at least cold dark matter. So clusters are highly nonlinear and complicated. If you can see this, the predicted different distribution of luminosity compared to mass, this would be, again, a direct probe of dark matter, because in order for the dark matter to be distributed differently from gas, it has to exist in the first place. But it would be in the linear theory on very large scales. Okay, so since I'm out of time, let me just briefly show you the results. So what we measured is the correlation function based on weighting by number density or by luminosity density. And you expect a difference because in the luminosity you have this additional effect. So it's hard to judge from this. This is a correlation function multiplied by distance squared, by separation squared. It's hard to judge here because of the strong covariances. Formally, we found a 3 sigma effect. So this is this bias parameter, and it's measured to be different from 0 at about 3 sigma. However, the conclusion is that we don't really believe this result, because so the main thing is to look at the difference between the luminosity weighted and number density weighted correlation function. This difference is these two quantities are based on the same galaxies, so their difference is actually what is measured accurately. And this difference you can see, so there are 3 models here. 2 of them actually are on top of each other. If you just include this, allow for this new effect to occur, it's not measured. The only reason it's measured at 3 sigma is when we allow another thing, which is a kind of a speculative thing called CIPs, compensated isocurvature perturbations. It's a kind of perturbation where dark matter and baryon fluctuations are opposite and canceling each other to leave the same total density. And because the total density is what determines gravity, these CIPs are very hard to constrain observationally. So this, in principle, constrains them because it measures dark matter and baryons separately. But it's only when you allow these CIPs is where you get a detection of this effect. But you can see that the detection, which is this one, is driven by very large-scale data where also I've been talking with Daniel today. So on large scales, there seem to be weird things in the data. So this is probably a systematic thing which we have to try to understand. And also the results were sensitive to the number of radial bins, so they just don't seem robust. So the summary is the question whether baryons follow the dark matter. So Avi and I realized that there's a new effect that people hadn't looked for in galaxy redshift surveys, which is so one way to isolate it is to look at the luminosity weighted compared to the number weighted correlation function or power spectrum of galaxies, and then you should see this effect due to the large scale variation, the leftover variation of the baryon fraction. So our conclusion is that current data statistically should be able to detect this, but we still need to understand systematic differences between the model and the data. But in principle, this is something the community should work on because it would be a very nice confirmation of the standard cosmological model and of the existence of dark matter. So thanks for listening. There, I think.
Could you repeat, what's your argument about the bullet cluster? I didn't get, what's your point about it?
Well, the bullet cluster people point to as, people say that there's some alternative models that try to, instead of dark matter, try to change change gravity. So the question is, how do you prove directly that dark matter exists? And this was supposed to be a nice proof that the dark matter, based on weak lensing, is seen to be, so this is 2 product clusters that pass through each other. The dark matter passed through itself because it's cold and collisionless. So it's where the galaxies are far away from each other, while the gas stuck together with itself in the middle. However, the bullet cluster becomes, so that seems to be like a strong proof, but then you have this counterexample, which means that something is going wrong. So it makes the bullet cluster much less of a proof if you find the opposite case. Yeah.
Dark matter goes back into the return phase, right? Because it's emerged and they fly outwards, then the dark matter returns, but the gas can then still be leaving on the outside.
Okay, maybe. So I don't know.
The dark matter returns again because in the end the thing has to merge, right? So the dark matter halos fly out and then they are on an orbit and only return.
No, but I think the question is why would the dark matter ever be differently distributed than the galaxies? Because the galaxies also follow the potential. I think that's not so simple. I don't think anyone has produced a convincing thing from simulation or something that would look like this. Because that's the question. It's not only compared to the gas, but compared to the galaxies especially.
Well, let's thank our speaker again.
Okay.
Okay, well, it's very nice to be back. Thank you for having me. So many of you work on X-rays or X-ray related science, but I'm not sure how many of you have heard of NICER. So just in a word, NICER's day job is going to be spent up on the space station measuring the masses and radii of neutron stars to determine equation of state with very high precision. But what I'm most excited about is what NICER can potentially do moonlighting on stellar mass black holes. And so that's what I'm going to be telling you about today. Just to briefly recap what NICER is about, it has 56 silicon drift detectors, and as those of you who've worked with Chandra or XMM, Suzaku will know, silicon is sensitive in this sort of 0.2 to 12 sort of keV range. So it's a great soft X-ray detector. What's really amazing is that it has timing accuracy down to 100 nanoseconds and better. So just to impress upon you how extreme this is, the previous champion of X-ray timing instruments was the Rossi X-ray Timing Explorer, and RXTE's timing precision was about a factor of 100 worse than NICER. So this is really a new sort of domain, and it's so impressive that they're using it actually to figure out the future of celestial navigation. So that's part of how NASA supported this mission. Well, okay, so thank you. Right, it's still very, very impressive here. So the one sacrifice that is made in building an instrument like this is NICER cannot do imaging. It's a collimated detector like RXTE before it, but it has 100 times more sharp pointing, which means that it'll have 1% the background of RXTE, essentially a negligible background. And its effective area-wise, it's about twice the size of the XMM PN. So it's a big light bucket that's focused at soft X-rays. Now, the reason that this is very important for studying stellar mass black holes is because while it's great for looking at relatively faint sources too, it has no pileup for even the brightest of X-ray sources. And this feature, for those of you who've dealt with scheduling X-ray imaging, you'll know this is very important, and particularly so for the brightest objects in the X-ray sky. So in figuring out what NICER will do for stellar mass black holes, the groundwork is really paved by what RXTE has given us. So this is showing you an accumulation of 16 years of RXTE observations of stellar mass black holes. This is in color intensity space, so the X-ray HR diagram, roughly speaking. And the color coding on this plot is showing you RMS timing information. So that is a sort of average flicker noise in the different data points. And you'll see that this rainbow traces very nicely with the hardness, that is the X-ray color. And so this is telling us that X-ray spectral states and X-ray timing states are intrinsically linked in a way. And the way in which this all must come out physically is from a very simple but complicated interplay between, simple because it's two systems, but complicated because it looks like this. Just two components, we think, just an accretion disk and a corona. But something about that interplay and perhaps changes in the corona or changes in the disk gives rise to that great wealth of behavior. So this is what we're trying to understand, and NICER can do some new things for us. So I just want to give you a brief comparison of the RXTE and NICER spectral capabilities and then their timing capabilities. This is showing you what I'm most interested in studying about black holes, that is the thermal disk of those two components. And you see here this is a very typical thermal spectrum or soft spectrum of an accreting black hole, and it's completely dominated by this thermal disk. And RXTE is giving us data right here in the wean tail of the disk, and it's also nice and sensitive to what's going out in the Compton power law. But if you're interested in studying the disk directly and maximizing your information about what happens from the disk itself, you might want something that's sensitive in this range. And this is what NICER will be showing us. So you see, you have an instrument in NICER that is really dedicated to studying accretion disk physics. And that's what's very important for us. So I already told you that NICER has 100 times, roughly, better time resolution than RxTE. And the only two things that matter for doing timing analysis are time resolution and your count rate. It turns out that even though NICER's effective area is smaller than RxTE's by a factor of a few, because it's sensitive to soft X-rays, which is where most photons are emitted from black hole systems, when you look at what the count rates you get from NICER compared to RxTE for a typical black hole system, this is the prototypical black hole system, GX339, you actually win essentially everywhere with NICER. And I was really stunned to see this, and it's fantastic news. So it means that when the black hole is in a soft state, NICER will do a factor of maybe 5 times better, and when it's in the hard state, they're very comparable. So this is great news. And the major punchline I want you to take away is that for timing analysis, NICER will meet or beat RxTE essentially everywhere. So what can we learn from the time domain? This is, of course, where the NICER's bread and butter will be. Well, to me, one of the most exciting frontiers in timing analysis is searching for these high-frequency QPOs in stellar mass black hole systems. So this is very exciting because there are about 5 of the 20 or so that we know that have shown high-frequency QPOs with a 3-to-2 resonance. And this has been mysterious and baffling, and there are many more models for what might have done this than there are data points for these things. So there are many explanations, and many of these explanations rely on the orbital frequency of the ISCO and different processes which might excite excitations near the ISCO that tell us something about black hole spin. So whether or not these high-frequency QPOs actually have a meaning that relates to black hole spin or not is still open, but it's certainly in the right sort of domain, and there are many folks who think so. We'd like to get many more data points than just these 5 systems, and NICER is the instrument that's keyed up to do this. So we're hoping that it will give us a completely new view and a disk-centric view of what's going on here. I should say that essentially all of those models rely on instabilities in the disk itself, not something to do with the corona. So NICER will be very sensitive to test that. But in addition to those high-frequency QPOs, there's in hard states, there's ubiquitously a low-frequency QPO that's at sort of a few hertz. And this low-frequency QPO is generally pretty coherent. There are actually a few classes. Some of them move with luminosity, some of them are static. There's a lot of rich behavior, and I'm not going to walk you through that phenomenology, but what I want to impress upon you is that in the same way that reverberation mapping has been giving us great insight into the geometry and structure of the corona and the disk in supermassive black hole systems, we'll be able to start probing this sort of thing by looking at hard and soft X-ray lags and doing reverberation mapping using NICER to probe spectral timing space for stellar mass black holes. And again, this tells us something important about the geometry of the disk and corona. There's one very important forefront question right now that's been the center of a lot of controversy in the field of accreting stellar mass black holes. This is the question of disk truncation in the hard state. So there are some camps which say that in the hard state, the accretion disk extends all the way down to the ISCO, and there are groups that say, no, the accretion disk truncates at tens or hundreds of Rg in the hard state, and it's only in soft states that it goes all the way down to this innermost stable circular orbit. And this has really profound implications for measurements of black hole spin and state transition and a lot of sort of the exciting fundamental physics that's going on in these black hole systems. And presently there are sort of 3 constraints that one can use to test this. So one is relativistic line broadening, another is sort of the disk temperature itself from the continuum spectrum, and one that has been underused is the net photon counting. So this is sort of preserving photons that come from the disk, scatter in the corona, and then may return to the disk, produce reflection. Basically, accounting for all of those photons that come out turns out to give you an important constraint as well. So glossing over the details, NICER will be sensitive in a domain that sort of lets us use a new suite of self-consistent models to address this question. And just to illustrate this, this is showing you simulation of just a short 2 kilosecond snapshot for models which cannot be reconciled with the highest quality RxTE data. So this is assuming a mildly truncated disk being compared to a non-truncated disk, and you see that in 2 kiloseconds you have all the signal in the world to rule one model in and one model out. So this will be a new day for sort of addressing this most fundamental of questions right now. I'm going to skip ahead and just want to highlight something exciting about reflection spectroscopy. That is, the usual view of X-ray reflection from black holes has been an iron line alone. But we are now in the age of new star. So if you've seen a paper that addresses spectral reflection lately, it's looked like this, and you've seen the iron line and a Compton hump. So where NICER is, I hope, going to take us is one step further. So we're going to add one more feature, and that is the oxygen line. This oxygen line turns out to have 10 times the photon flux of the iron line in the sort of specific window of ionization that one gets from stellar mass black holes. So this isn't something that you get from AGN, unfortunately, but it's in the soft X-rays peaked just about a factor of 10 below the iron line. And so just to highlight for you, this is a beautiful spectrum here with very high signal showing the iron line and Compton hump. And this is huge signal. But if one looks at a ULX that's relatively faint, and then the residuals here for a model that doesn't include reflection, you look in the iron band and you see nothing. But here I'm showing you what it might be producing in oxygen and what NICER can detect in 100 kiloseconds. And you see this oxygen residual is again screaming at you. So I hope we'll add oxygen sensitivity and maybe be able to get reflection measurements and detect inner radii from oxygen. So with that, I want to just leave you with one exciting thought, which is that spin is being measured from stellar mass black holes. I should say it's being probed in stellar mass black holes using 3 techniques, 2 of which are really measurements, and 1 of which is hopefully going to be a measurement shortly. There's continuum spectroscopy, reflection spectroscopy, and in the near future, hopefully QPO timing. NICER is uniquely the instrument that can use all 3 techniques and potentially even all 3 at once, which is sort of a cute capability and hopefully will actually be realized. So I'll flash up this list of what NICER can do for you and take any questions. Thanks. January next year. So originally it was going to be this August, but delays in the SpaceX Dragons have pushed it back. But in January, it's slated to go up. Actually, Friday the 13th.
So Jack, the oxygen line, that's very exciting. That you could actually do stuff with that. Now that is of course well below a KEV, and the hydrogen column will probably kill it in some sources.
Yes.
I'm just wondering, in our galaxy, you take all the usual culprits, all the black hole binaries. What fraction of them are sufficiently, unabsorbed that the oxygen line can be probed?
No, that's a great point. So it's very sensitive to NH. So when you get to an NH above about 0.3, then the 2 lines are very comparable to each other. Sorry, 0.3 times 10 to the 22.
Okay.
So 3 times 10 to the 21. And there are only about 3-4 stellar mass black holes that are in that very low NH regime. But for extragalactic sources, especially nearby ones, there are many. So the hope is that it can really give us something where we don't have enough signal in the iron line for those.
Thank you.
It worked before, I swear. All right, bear with me. Sure. Okay, so it's on Dropbox. Could I borrow your computer?
Oh shoot! Actually,
Password?
well, yes, but I'm not sure I'm connected here. Let's see if
I just need to turn on the Wi-Fi, I guess.
Okay. Okay. All right, let's go with this. And now for something completely different, I'm going to talk about modeling hardware. So most of you should be familiar with the mission concept of the X-ray Surveyor. So this is a notional successor to Chandra. And I work on the optics, so I'm going to talk about simulating the optics. So this is a little cartoon of what the Chandra optical system looked like. You had 4 nested optical shells. The X-rays went through two bounces, and then were focused down onto a CCD. Okay, so Chandra used 1-inch thick glass substrates. These were very heavy, expensive to launch. So the idea for the Surveyor is to use lightweight optics that are tightly packed to maximize collecting area for a given launch mass. The mirror pairs will be aligned and bonded into modules, at least for the approach that SAO is proposing. So the idea is that you fabricate thin, lightweight mirror segments. Those are then aligned and bonded into modules, which are then themselves aligned and bonded into a telescope assembly. The challenge here is to fabricate these subarc-second mirrors and maintain subarc-second performance even after bonding and launch. So the way that SAO is proposing to do that is to use piezoelectric adjusters. This cartoon right here gives the concept. Many of you have seen this before. We start with a 0.4 millimeter thick glass substrate. We slump that down to the notional Wolter 1 geometry, deposit a reflective X-ray coating on the front. On the back, we use a continuous platinum ground electrode followed by 1.5 microns of piezo material. We're using lead, zirconate, titanate, and then segmented platinum electrodes on the back of that. this is a photo of one of our early prototype mirrors. It's a 220 millimeter radius of curvature segment, and you can see the cell pattern on the back. And so the idea here is that when you apply a voltage across the piezo material, it wants to contract in the plane of the mirror. And so if you mount and bond the mirror in an over-constrained fashion, you can create localized distortions, and you can control the figure of the mirror. We're also planning to use on-cell strain gauges, and so it's essentially a resistor whose resistance depends on local strain. You can imagine if this coiled trace undergoes strain, the traces get longer and narrower, and so the resistance changes. If you hook that up to an external electrical system like a Wheatstone bridge, you can measure resistance as a function of strain. Okay. So this requires optimizing the mirror figure, the figure of each mirror using the piezos. So the general strategy here is to obtain the figure measurement of an individual mirror, calibrate all of its influence functions for all the actuators, then determine an appropriate merit function to use to evaluate the PSF due to the present mirror distortions, then use this optimization algorithm to compute voltages to minimize this merit function, and repeat for all mirrors in the system. Okay, so this is a numerical linear algebra problem. You can formulate this into a simple least squares linear algebra equation, and there are many packages that exist to attack these sorts of problems. I'm currently using a sequential least squares programming routine that was written, I think, in the 1980s in Fortran, but there's now a Python interface to it. I can get this routine to compute the merit function and its derivative in parallel, but the part of the algorithm that then computes the next iteration of voltages to try, that runs serially. So I know that sequential least squares programming uses numerical linear algebra under the hood, and so theoretically that can be parallelized. Task for the future is to search for either a faster commercial solution or even maybe a solution that currently exists amongst our colleagues in visible adaptive optics. Or perhaps what would be more fun is to write my own. Either way, this is needed for X-ray Surveyor Monte Carlo simulations. What we have right now is okay for our current technology development tasks, but if you're going to simulate an X-ray Surveyor that has something like 8,000 mirrors, we are going to need something that runs in parallel. Okay, also the choice of merit function is not completely straightforward. To date, we've been using just brute force RMS slope in the axial direction on our mirrors. But the problem here is that weights all spatial frequencies equally. You can imagine if you have a regular cell pattern that you're using to control the mirror, there's obviously a Nyquist frequency above which you can't correct. And furthermore, you're going to be correcting based on metrology, which has high frequency noise. Okay, so it's clear that for potentially weighting by spatial frequencies can improve the optimizer performance. Also, less obviously, is that the presence of this regular cell pattern on the mirror can create what we call print-through ripple. What I'm showing here is a figure measurement of a flat piezo adjustable mirror after filtering out the first 70 Zernike polynomials. And you can clearly see a regular distortion ripple that's due to the stress of that platinum. Okay, so it also turns out that this print-through ripple occurs in a spatial frequency called the mid-frequency band, where physical optics starts to become important. Okay, so scattering theory in a nutshell. Suppose you have an optical surface that focuses light down into a nominal point, and then you put a sinusoidal distortion on that surface. If the frequency of that distortion is very low, you would get a point spread function that looks like this lower right plot, which is just the slope distribution of the sinusoid. If you increase that frequency to the high frequency range, that then acts like a grating, and you get a characteristic diffraction pattern, just like with classical grating theory. But then in the mid-frequency band, there's a continuous transition between the two where you get sort of a mixture of the two effects. And you can't use grating theory to predict that, and you can't use geometric ray tracing. So you have to do some sort of diffraction analysis. Okay, so the way this was typically done for the Chandra days, or the AXAF days, was to choose a cutoff frequency between grating scatter and geometric ray tracing. So in this panel right here, you can treat the low frequency distortions as simply a distorted surface where the angle of reflection equals the angle of incidence. For the higher frequency distortions in this panel right here, you can apply a scatter convolution to a ray that you're tracing based on grating theory. And for AXAF, they essentially chose a cutoff frequency where they took all of the distortions below that frequency and modeled surface deformations and did geometric ray tracing. And then they took all the frequencies above that cutoff and applied scatter theory. And this worked well. The PSF measurements matched predictions, but it was also fairly insensitive to the specific choice of that cutoff frequency. But when you use piezos with a regular pattern to correct a mirror, you can get sharp peaks in the surface power spectrum after correction. So what I'm showing here in blue is an original pre-correction power spectrum of an X-ray Surveyor mirror, and then in green is the power spectrum after applying piezo correction. So you can imagine if you take this cutoff frequency and you apply it before or after one of these peaks, you can introduce or take away sharp features in the point spread function that you predict for the telescope. Okay, so there's work that's planned to incorporate the scattering theory into both the optimizer merit function and also the techniques that we'll use to simulate the full X-ray Surveyor in the future. Okay, so this work is essentially tuning the scattering convolution. Just simply because of the short wavelength of X-rays with respect to the spatial dimensions of our mirrors, full Fresnel diffraction is computationally expensive. So we'll rely on ray scattering convolutions instead, but we'll tune our scattering convolutions using rigorous diffraction analysis on theoretical mirrors. So due to the grazing geometry of X-ray telescopes, axial figure error dominates by about 2 orders of magnitude. So there's a formalism due to some colleagues at the OAB, the observatory in Brera in Italy. They're using axial slices of the mirrors, diffracting the incoming light onto an axial slice on the primary, then diffracting that onto an axial slice on the secondary, and then diffracting to the focal plane, and then superposing the point spread functions from the various axial slices. So this formalism can be used to put the scattering convolution technique on firm theoretical ground to make sure that we are handling these mid-frequency features accurately. Okay. So finally, we'll be using similar techniques to simulate the X-ray Surveyor as a whole. The idea here is that you use a surface power spectrum to generate a random substrate error for all of the mirrors, run the optimizer algorithm to determine the corrected surface figure, then trace rays through the mirrors, applying scatter convolutions where appropriate. You add in random cell failures, calibration errors, misalignments, potentially noise on the outputs of the strain gauges, so on and so forth. Then you can determine telescope performance as a function of these various errors. And then you can come up with the requirements for the various aspects of the Surveyor. So GPUs, I plan on using GPUs for these Monte Carlo simulations. GPUs are very well suited for ray tracing, which is often described as an embarrassingly parallel problem. Okay, so summary. Codes exist for bounded least squares optimization, but we do need a fully parallelized version. Ray tracing is an efficient technique to do optical modeling, but we do need to ensure that we're handling the physical optics appropriately. And that also goes for the optimization merit function. And this is all going to be going on GPUs. GPUs are more accessible today by a lot than they were, say, 10, 15 years ago. And so I think for a modest cost, you can get a tremendous amount of computing power in your personal workstation and do simulations of this magnitude. So that's it. Yeah.
So how much ability will you have post-launch to fine-tune each individual segment?
Okay, so we'll have on-cell strain gauges that we can ping over the course of the mission lifetime. And so a primary objective of this is to actually measure any degradation in the piezoelectric coefficient of the various cells as the mission goes on. So if you can measure a degradation of this coefficient, you can perturb the voltages and correct for that. If you have the unfortunate situation of disruption during launch, I think your ability to correct for that depends on the magnitude of the disturbance. If you get completely lost, I think you're hosed. But if it's a small disturbance, there is potential to use the strain gauge information to correct.
First, what's the time scale, do you think, for being able to demonstrate this with an actual model? And two, what competition is there, other ways of doing the same result?
Oh, that's a loaded question. So our time scale internally to demonstrate this technology is on the order of a year from now, doing an X-ray test at Marshall with a co-aligned adjustable mirror pair. There's lots of competition. There's at least 4 or 5 different groups across the country working on this problem. Goddard is working on static single crystal silicon mirrors. MIT is working on air slumping on air bearings. Northwestern is using magnetic adjustability. So there's a lot of ideas out there, and I forgot at least a few.
Pretty well, but yeah. There's been a little bit of work put into that. Before my time, they took a look at like a bridge, bring a pattern, use a hexagonal pattern, that sort of thing. It hasn't been exhausted, so there's more work to be done. But what we do know, the regular pattern should work. We've got simulations using the FEA that if you start with about a 10 second mirror, you can bring it all the way down with the cell pattern we're proposing using. The problem with the cell patterns is it requires a lot of FEA and a lot of computation time. So every time we want to do new geometry, we've got to have an engineering central engineering with all these different before you. It's expensive.
No, I know. But he will have more than 90 seconds.
It's sort of like the NASA way, right? If you find something that works,
I'm not going to go. See you later.
Right.
Got it. No, very, very good. How are you doing?
Hi. Did you ask you?
Yeah, we'll come back. Nazma, sorry.
I'm sitting there with my long sweater.
Visitor,
I think that
for a
computer's
month
about
working with software.
it's like
Great.